this lecture is Mesoporous materials and their sensing applications. Mesoporous materials are smart materials or intelligent materials. Porous materials are of great interest because of their ability to interact with atoms, ions, molecules, and nanoparticles, not only at their surface but also throughout the bulk of the materials. There are basically three types of porous materials: micropores, pore size less than or equal to 2 nanometer, for example, zeolites; mesoporous materials, pore size between 2 to 50 nanometers, for example, KIT6, SBA15. KIT6 and SBA15 is a type of silica, SiO2. KIT6 is Korean Institute of Technology. It was investigated in 2004. And SBA15, Santa Barbara Motion Materials, it is also smart materials. And it was investigated in 1998 at California by Dejau. And macroporous materials, pore size greater than 50 nanometer, for example, cotton, sponge, etc. Mesoporous materials, the overwhelming tendency for solid to minimize void space within their structure is inherent. Porous materials are difficult to make artificially, but Einstein say in the middle of difficulty like opportunity. The above statement was made true by mobile scientists in the year of 1992 by successfully synthesized mesoporous materials MCM48, MCM41. They are mobile crystalline materials. These are also type of silica. Mesoporous materials can be ordered or disordered depending upon their chemical use as source for silica, surface tension type, pH, their physical condition, temperature, and synthesis methodology also depend. Can yield different type of mesoporous materials. Mesoporous silica is the most studied and well-known mesoporous materials. Since silica is ideal for controlling the structure, texture analysis, and shape of final materials, and also present the advantage of being safe for medical and biological applications. Advantage of mesoporous materials: because simple silica has surface area nearly 175 to 225 meters square per gram, but mesoporous materials, for example, SBA15, MCM48, surface area is more than 1000. So tunable pore diameter, large pore volume, narrow pore size distribution, interconnected pore channels, high thermal and mechanical stability up to 600 degrees Celsius, biocompatible and low toxicity, easy and rapid transmission of water vapors and charge carriers. Major research finding of mesoporous silica: in 1992, Mobile Oil Company brought a revolution with the synthesis and ordered mesoporous molecular sheaves M41S. This is a family of a MCM48, MCM41 like this from liquid crystal template. Of particular mention is the remarkable finding by Dejau et al. Regarding the preparation of large pore ordered mesoporous silica with a two-dimensional hexagonal structure by using a tri-block polymer as template, which is very well known as SB15, KIT6, MCM48, and all M41S families. Further, in 2003, KIT6 discovered by scientists of Rao Group and block copolymer and butanol were used to synthesize large mesoporous siliceous materials exhibiting cubic 1A 3D symmetry. COK12, also family of mesoporous materials, Center for Surface Chemistry and Catalyst. The structure of COK12 is characterized by its hexagonal packed cylindrical ordered pores, which have a diameter of 5.5 to 6 nanometer. In 2000, a new mesoporous materials, this is also smart or intelligent materials, TUD1, invented at DUT, Delft University of Technology at Netherlands, which has a sponge-like disordered mesoporous structure. Synthesis of hybrid nanocomposites. There are various synthesis techniques. For example, top-down technique will start with bulk materials and then break it into small pieces using mechanical, chemical, or other form of energy. Grinding or milling is a typical example of top-down method in making hybrid nanocomposite. Secondary, bottom-up approach, in which nanomaterials are synthesized from atomic or molecular species via chemical reactions. Soldier colloidal dispersion hydrothermal is a good example of bottom-up approach for synthesis of hybrid nanocomposite. There are different routes for synthesis of mesoporous materials: hydrothermal, sol gel, sputtering, co-precipitation, nanocasting, many more. The above mentioned approach may be further classified in terms of physical or chemical techniques. Physical techniques is based on a process of transferring gross species from a source or a target. The process proceeds automatically and mostly involve no chemical reaction. In physical technique, chemistry is poor, but in case of chemical techniques, various type of chemical reaction are involved, and chemistry is very rich. Sol gel or hydrothermal is one of such technique and has been used to produce hybrid Mesoporous nanocomposite. Sol gel, Sol gel process a cost-effective, versatile, and stoichiometrically homogeneous control of doping can be easily achieved. Sol gel, definition of Sol, state of distribution of colloid particle in liquid state is called solid. The colloid particle through van der Waals interaction connect to form three-dimensional solid network is called gel. The Sol gel method is wet chemical synthesis technique for preparation of glasses, ceramics, and hybrid nanocomposite or Mesoporous at low temperature. This is a merit of Sol gel techniques. It is based on control of hydrolysis and condensation of alcohols precursors. Generally, three steps are used to describe the Sol gel process. First, hydrolysis, alcohol condensation, and water condensation. This is the first step, hydrolysis. Here, alkyl group is hydrolyzed during hydrolysis reaction. The alkoxide group are replaced with hydroxyl OH group through the addition of water. Second step, condensation. After condensation, SiO network are formed. Next, third step, after aging and drying, water and alcohol are expelled, and SiO network are eventually result in a SiO2 network. This is the second hydrothermal Mesoporous synthesis procedure. Here, this first step, polonic P123, tribalocopolymer, add P123 plus HCl as a catalyst to pass the reaction plus water as a solvent. After 4 hours stirring at 40 degrees Celsius, add X means metal or metal oxide. After 2 hours and 40 degrees Celsius, add TO. This is a source of silica, tetrahydroxysilicate. After stirring 24 hours at 40 degrees Celsius, gel product formed. After this step, hydrothermal treatment at 100 degrees Celsius for 24 hours. After hydrothermal treatment, you get a filtered and washed that at 80 degrees Celsius, calcined at 600 degrees Celsius, and Mesoporous SBA15 hybrid nanocomposites are formed. This is in the form of powder. This is synthesis of SBA15 by hydrothermal treatment. Here, this is your micellar solution, transport Teflon beaker. Autoclave is then put into hot air oven at 100 degrees Celsius for 24 hours. This is autoclave. In oven, autoclave is then removed from oven and cooled down to room temperature. At this stage, solid product recovered, washing and calcination. After that, we get Mesoporous SBA15 or KIT6 like powder form. Characterization technique, summary of tools for materials using chemical or physical characterization. If you determine a composition, you get a composition analysis. You will use XRD. There are two types of XRD, wide angle XRD or small angle XRD. If you want to elemental distribution or local chemistry, then SEM with EDX are required or HRTM with EDX. If you want to know about information from surface or interface chemistry, then XPS or FTR are needed. If you want to change phase of your materials, then STA, simultaneous thermal analysis, or TGE, thermogrammetric analysis, DTE, differential thermal analysis, and DSC are used. If you want to determine information from surface analysis, then BET are required. Post and pore ordering, we need small angle neutron scattering and small angle X-ray diffraction. In case of neutron scattering, electromagnetic radiation interact with the neutrons and protons in nuclei, and in case of small angle X-ray diffraction, electromagnetic radiation interact with surface of atoms, not in neutrons and protons. Particles, if you want information, particle or grain size distribution or morphology, SEM and quantitative TEM and XRD are used. Phase identification and molecular structure, XRD and FTR analysis are used. Above list some of the technique that you might consider to obtain specific information about your material. In characterizing a sample, whether it is single crystal, polycrystalline or glass, there are certain type of information that we are interested in obtaining. If you want to chemistry of your materials, what is the composition, how does it vary within the sample, etc. If you want to know structure of the materials, are the materials crystalline or glass or a mixture of the two? If you want to microstructure analysis, it is the structure the same throughout the sample. Polycrystalline materials cannot be uniform. Even glass can be strictly inhomogeneous. For surface analysis, I already explained BT analysis as used. In case of nanomaterials, the surface is the most important feature since most of the atoms are there. The surface analysis of characterization techniques is a very important part of material synthesis, which present the quality of materials prepared, such as material surface, porosity, size, morphology, and surface area. Various characterization techniques such as SAM, TEM, EDX, STM, or low energy electron diffraction. Most of the techniques we describe here can be used to study the different class of materials and surface analysis of the materials. The suitability of a characterization techniques depends on the type of information we hope to obtain and may also be dictated by the size of our sample. What part of sample is important and whether we can destroy the sample. There are some limitations in characterization tools. For example, in case of reflection techniques, examine only surface. Techniques using electrons require the sample to be in a vacuum. Some techniques are used vacuum, and some techniques are used in work in presence of air. Techniques using transmitted electrons generally require the sample to be thin. For nanomaterials, we need high resolution. We always ask two questions: how much materials is required for the analysis? Is it destructive or non-destructive? For example, HRTM is invariably destructive, but you need a very small amount of materials for the analysis. Wide angle XRD, I already explained there are two types of X-ray diffraction techniques, small angle and wide angle. In case of wide angle XRD, in actual XRD techniques are used to determine the crystalline of pure materials. In case of wide angle X-ray diffraction analysis was used to study the crystallinity of the powder sample. This method can be used for phase identification, structure analysis, grain, and unit size determination. The value of interplanar spacing were estimated using Bragg's law, 2D sin theta equal m lambda. Everyone knows about the Bragg's law. And with the help of JCPDS card, you can identify million indices or planes of your materials. Another PCPDF is another software. With the help of this software, we can identify and we can standardize your materials. The approximate crystalline size was determined from the XRD data using Searle formula T is equal to 0.9 lambda upon beta cos theta. Beta is the physical significance of this formula is beta is full width and half maximum, theta Bragg's angle, lambda wavelength of electromagnetic radiation, value of K is equal to is 0.9 and D diameter of your particles. Next, small angle XRD, small angle X-ray scattering is a widely used technique to study large scale inhomogeneous in a medium at a length scale much larger than the wavelength of X-rays. It has been put a variety of uses such as measurement of size of particles dispersed in a solvent, investigation of the structure and conformational change of biological macromolecules, determination of interaction parameter in fluid, and estimation of internal surface of the porous materials. That in case of small angle X-ray scattering, we can identify the pore order of your materials. Normally, pupils are not using this small angle XRD. Those people who are working in the area of porous materials, these people are using small angle XRD because small angle XRD or small angle X-ray scattering are used to determine the pore order, pore structure of your porous materials. On the other hand, there are no sharp Bragg peak in small angle X-ray scattering and only an intensity profile smoothly varying with the scattering angle is obtained. In case of small angle XRD, the Kratky camera is used. With the help of this Kratky camera, we can identify your pore order. On the one side, the intensity drops down sharply and data can be collected at a very small angle of the order of 0.02 degree close to the main beam. Specialized equipment is required to study small angle X-ray scattering where the incident X-ray beam is very near sharp. These are two spectrum of low angle XRD and small wide angle XRD. This is the spectrum collected from low angle XRD. Here at angle 0.9 degree, we can identify this plane, 100 plane. And wide angle XRD, the sharp peak in case of small angle XRD, just hump are observed. But in case of wide angle XRD, we can determine sharp peak like this at 28 degree, 35 degree like this. These are sharp peaks of metal or metal oxide. Next, scanning electron microscopy are also used to determine the average size, not the exact size, and surface morphology, particle in the form of shape, structure, and topography. the arrangement of natural and artificial physical feature of the area of the samples. There are some parameters of SAM techniques: accelerating voltage, 20 kilovolt, probe current, 0.3 nanoampere, working distance from your sample to probe, 7 to 50 nanometer, sorry, mm. Magnification range 500 to 10,000. Same with EDX. EDX also very important tool to use for the elemental analysis or chemical characterization of the samples, the materials. This is a spectrum of EDX. With the help of EDX, we can identify elemental analysis. For example, in our sample, silver, this is tin, this is tin, this is oxygen available in my materials. This is a photograph of SAM, and inside we observe this is a EDX spectrum. This is also SAM photograph. HRTM. HRTM are also important techniques to determine the surface morphology, surface topology, average, not average size, this is exact size of, you can identify exact size of your materials. Because in case of HRTM, electrometry radiation are transmitted through the sample. But in case of SCM, electrometry radiation incident on surface of the materials. UV visual spectroscopy is also important tool to determine the band gap for your materials. In case of UV visual spectroscopy, deuterium discharge lamp for UV measurement and tungsten halogen lamp for visible and NIR measurements. This is a schematic diagram of UV visual spectroscopy. This is source, this is monochromator, this is slit, and this is reference cuvette, this is solvent, and this is your sample detector, and this is record and display. Record and display may be your computer and your person as a person. Infrared spectroscopy is also important tool to identify the Mesoporous materials. It is generally subdivided into three regions. IR region 12,500 to 4,000 centimeters, mid IR region 4,000 to 400 centimeters, and far IR region 400 to 50 centimeters. The infrared spectroscopy is a powerful tool for identification and characterization of organic, inorganic, polymeric, crystalline, and coordination compounds. The mid-IR region is very important. Most commonly, pupils are used in this range 4,000 to 400 centimeters. The far IR region is also equally important when dealing with inorganic compounds. An infrared spectrum has four main features: the number of bands present. You can determine number of bands, wave number of positions, shape of the bands, and intensity of the bands. Application of Mesoporous materials. For example, sensors, humidity sensor, gas sensor, temperature, there are various types of sensors. In layman, sensor is a device which measures a specific chemical, physical, or biological quantity and convert it into a useful electronic signal that can be read by an observer or by an instrument. Sensor specification. Sensor specific of sensor is sensitivity, selectivity, stability, detection limit, dynamic range, working temperature, repeatability, response time, recovery time, hysteresis, linearity, and life cycle. Need for humidity sensor. Why do we need this humidity sensor? There are two types, RH and AH. Food processing, storage, paper column, textile industries, medical industry, sterilizer, incubator, storage of artificial limbs, pharmaceutical and drug industries, library, museum, research laboratories, airplanes, submarines, computer, mobile phones, and sophisticated instruments, manufacturing industries, household applications, for example, refrigerator, AC, vehicles, cooking control or microwave ovens, and living environments. Humidity has key environment concern, effect of higher humidity and effect of lower humidity. Effect of higher humidity, air becomes waterlogged, slow perspiration, feeling more hot than actual, high risk of hyperthermia, heat stroke is more likely, vomiting, dizziness, headache, muscle cramps, rapid drop in blood pressure. Effect of low humidity occur in winter months, dry skin, irritated sinuses and throat, and itchy eyes, increase the risk of colds, flu, and other infections. Evaporation of tears, which causes irritation in eyes, and skin cracking. Impact of present work on design of futuristic RH sensor. RH sensor, relative humidity sensor based on SBA 15 nano hybrid will possess following attributes: easily to synthesize and design, excellent performance at room temperature, wide range of relative humidity percentage detection 11 to 98% RH range, high accuracy, robustness, and low cost, ultra fast response and recovery times. High sensitivity, selectivity, and hydrothermally stable. Highly durable and stable over long period of time, negligible hysteresis, and easy reproducibility. Existing materials for sensor-related issues. Materials can be classified into three types: metal, ceramics, and polymers. For ceramics-based, brittle, short lifespan, long recovery time, sensitive to dust and smoke, poor selectivity. Polymer-based mesoporous materials, poor hysteresis, non-linearity, poor selectivity, easily degradable, short life, require heating after prolonged time of usage. At last, semiconductor metal oxide, sensitive to both reducing and oxidizing gases, poor sensitivity at high temperature, and need more power, low accuracy. Advantage of mesoporous materials, for example, advantage of SB15 Santa Barbara. This is Santa Barbara amorphous materials. This is a type of silica. It was investigated in 1998 by D. Zhao. Surface area of SB15 is 800 to 1000 meters square per gram. Tunable pore diameter, large pore volume, narrow pore size distribution, interconnected pore channels, excellent shock resistance nature, high thermal mechanical stability, easy and rapid transmission of water vapor and charge carriers, support micropores which reduces the chance of dead ends. This is a fabrication of sensing element. This is a fabrication of sensor. This is my sensor. This substrate, this is AGPD substrate. This is 5 pins. The substrate consists of 5 pairs of AGPD interdigital electrodes printed on top of the ceramic substrate. This is ceramic substrate and the top pin AGPD substrate. And a volume of this 3.4 mm to 7 into 0.5 mm. Each powder sample was mixed with water to form a paste. The paste was drop coated on the substrate. This is drop casting method. With the help of this drop casting method, we can deposit a thin film on this substrate. The coated substrate was then dried at 80 degrees Celsius for 12 hours. This is my sensing setup. The control RH environment was generated by using airtight chamber. This is airtight chamber. 11 RH percentage, 33 RH percentage, 54, 75, 84, and 94. This is airtight chamber containing saturated aqueous salt solution. In this chamber, aqueous salt, different salt, different percentage. The sample coated substrate like this. The sample coated substrate was put sequentially into chambers with different RH percentage for the uptake of water molecules. This is keyless source metal and this is PC. This is a facial nanocaustic synthesis of mesoporous AG-doped acetone nanostructure with enhanced humidity sensing performance. Here at this step, we prepare ordered mesoporous silica. After that, we remove this mesoporous silica and coated tin surface of SB15. After that, we dope AG in these channels and it becomes mesoporous SNO2 replica. This is low angle XRD of this as prepared sample. This is bare SB15 and this dope SN dope and at last this is silver doped in SN. This is BET analysis of adsorption and desorption. This is type 4 curve, type 4 isotherm. With the help of type 4 isotherm, we can identify this is mesoporous. Type 3, type 1, the isotherm are not mesoporous. It means this is type 4 isotherm, this is mesoporous. BET results, this is surface area of bare SB15, tin dope, a soft template, tin dope, hard template, and this silver dope in tin, the pore diameter, pore volume. This is HRTM of this silver doped tin hybrid nanocomposite. This is also this is hexagonal pattern. In case of a SB15 silver dope, this is hexagonal pattern. This is hexagonal. One pixel is hexagonal pattern, benzene-like structure. This also is a TAM image. This is EDS analysis. The EDS analysis to determine the purity of your materials. Here, at this energy, Ag, tin, or oxygen. Here this is bare SB15, here simple silica or oxygen. But in second spectrum, silver, tin, and oxygen. This is linearity. This is humidity sensing curve showing the decrease in impedance with increase in RH. This is bare order of change less. This is soft template, hard template, and this silver doped SNO2. Here order of change, 5 order of change. 10 to the power 8 to 10 to the power 3. This is hysteresis. This is minimum hysteresis. Absorption and desorption. In between this 0.7, hysteresis curve showing absorption desorption response measurement in 11 to 98 RS percentage range for hard template. This is response recovery time of my sensor. 11 to 33 RF percentage. Response time 0.7 second and recovery time 2.2 second. Similarly, 11 to 54 RS percentage. Response time 1.6, recovery time 3.7. Similarly, at last 11 to 98 RS percentage. Response time 4 second and recovery time 6.5 second. 11 to 98, 98 to 11. At different RS percentage. This is comparison with other reported works. Order of impedance change, response time, recovery time, hysteresis, and this is my sensor, AG-SNO2 sensor. Response time, order of impedance change 4.5 order, response time 4 second, recovery time 6.5 second, and minimum hysteresis 0.7%. This is comparison with commercial RH sensors. These sensors are available in market. Response time, recovery time, hysteresis, and sensitivity range. But in my sensor, hysteresis, minimum hysteresis 0.7%. And response time is good and recovery time also very good. Conclusion. Highly ordered Mesoporous SNO2 and AG-SNO2 materials were synthesized using hard template of SBA15. The nanocasting pure Mesoporous SNO2 show 7.5 times higher sensitivity than conventional porous SNO2. The response time was further enhanced to 5.5 fold for AG-doped nanocasted SNO2. Because when SBA15 and SNO2, this is prepared by hydrothermal method. If we go through nanocasting, it becomes AG-doped SNO2. The AG-SNO2 nanocasted sensor exhibited a super rapid response recovery time 4 seconds and 6.5 seconds. Excellent linearity, minimal hysteresis, high stability, and high selectivity at room temperature. The result of this work will definitely go through high quality international journals. This work was published RSC Journal of Metal Chemistry A, impact factor 15.5. And sensor prototype based on this work will installed in department engaged in research lab activity in university for initial analysis and testing of the device. We will coordinate and collaborate with industry to commercialize our device and will carry out the process to next level for wide application society. The development of SBA-based humidity sensor will definitely count to be a step forward in the emerging field of RS sensor. I published one patent on the basis of this work. Design patent. This is design patent of humidity sensor. This is a facility available in my university and my department. In my department, gas sensing setup available, picometer, digestive setup, humidity chamber, humidity sensing setup, many furnace, centrifugal machine, spin coating, deep coating, LV system, DC, RF sputtering, UV visual spectrometer, cyclovoltmeter, ball milling, photoluminescence, MEMR, X-ray diffraction. In my university, atomic absorption spectroscopy, impedance analyzer, FTR, UV, TG, DTA, DSC, PVD coating, induction furnace, renewable energy test center, NMR, and HPLC. This is my research team. Thank you.